So in order to remind you a little bit of lumped elements, I want to start essentially by reminding you lumped element resonators. I know you have seen them from your undergraduate days or perhaps in different courses, that there are essentially two main second-order resonators that people have studied a lot. It's either the series one or the shunt one. And both of these resonators end up resonating at some frequency given by the square root of 1 by LC, at least for the low loss case, meaning when the losses are small compared to the energy stored in the resonator. And I know that you have studied quite extensively what happens to the impedance and what happens to the admittance and what happens to voltages and currents. So I won't really remind you of this. But what I do want you to remember is essentially a very important consideration which will become a critical figure of merit for us. And that's called the quality factor. So the quality factor as Q is a very general quantity that is essentially defined as practically the energy that you can store in the resonator versus the power that you have to lose per cycle. Ideally, this quality factor should be as high as possible. So ideally, we're looking for lumped element resonators to have quality factors as high as possible. Of course, infinity is a great number, but it doesn't occur in real life. But high Q is good Q. Now, in order to build such a good quality resonator, it is important to understand physically where energy is stored and where is power lost. So energy is always stored in the volume that you're storing your electric and magnetic field. So the larger you can make that volume, the better things are. And that's why typically large resonators, physically large resonators, tend to have higher Qs than small resonators. And that's why distributed resonators, cavity resonators, or transmission line resonators have better quality factors than lumped element resonators, because lumped elements are by definition tiny, small. Where do you lose energy? So first of all, you lose power by consuming it as heat in the metals, in the metal parts of the resonator. So ohmic losses is the #1 reason for losing power. The second part is you may have a lossy dielectric. For example, the substrate is a lossy dielectric. So if you end up storing electric or magnetic field inside the substrate, then you will also lose energy in the substrate, and you will find out that you have a warm substrate. And finally, as we were just discussing before, open space is suspect for radiation. So that means if you store E and H in an open space, you might lose them because of radiation effects. So when you try to minimize losses in a resonator, we typically try to minimize those three. Now, those three losses, though, are not the same as a function of frequency. For example, at low frequencies, metallic losses tend to dominate, while open space radiation is practically negligible. In high frequencies, open space radiation might actually be the dominant loss that you have. So you need to be careful of where, at which frequency regime each loss is actually important. Now, as I mentioned before, when you build lumped element resonators, you necessarily take a hit in Q. And that's because you're making a sacrifice of the volume. You're making the resonator tiny in order to basically fit it in the given space that you might have. And because you have limited volume, your stored field doesn't have enough area to take. Also, lumped element resonators have a ton of metal. You use metal to build your capacitances, you use metal to build your inductances, so there's plenty of opportunity for energy to be dissipated as ohmic loss. The good thing is they don't have much radiation, so you don't have to worry too much about it. Now, there are two types of lumped element resonators that you will find out. There is what I will call here the off-chip and the on-chip. So the off-chip resonators are the ones that you build with lumped element inductors that you can buy from the store and capacitors, and you just put them on a PC board. While on-chip resonators are the ones that you literally fabricate on a silicon or gallium arsenide or silicon germanium chip. And naturally, the on-chip resonators are much, much smaller than the off-chip ones, so they basically will end up having significantly lower Q than the off-chip resonators. But of course, they're also significantly smaller. And so a lot of the RFIC designers, what they try to do is they try to not go off-chip. They try to stay on-chip just because integrating everything on a single chip is the lowest cost possible you might have. You don't have to worry about buying anything off the shelf. You integrate everything, and they try to make sure that they can live with this type of queues, which sometimes can actually be as low as 5.